Good afternoon, everyone. We're pleased to have Professor James Rehg as our Mass AITC webinar speaker today. Professor Rehg is a founder professor of computer science and industrial and enterprise systems engineering at UIUC, where he leads the Healthcare Engineering Systems Center. His research interests include computer vision, machine learning, and mobile and computational health. Professor Rehg has authored more than 200 peer-reviewed scientific papers and holds 30 US patents. He previously served as the lead PI on an NSF expeditions project to develop the science and technology of behavioral imaging, and also as deputy director for the NIH-funded Center of Excellence for Mobile Sensor Data to Knowledge. In addition to leading the Healthcare Engineering Systems Center at UIUC, Professor Rehg currently serves as deputy director and core lead for the NIH-funded mHealth Center for Discovery, Optimization, and Translation of Temporally Precise Interventions, where I have the pleasure of working with him on that project. In today's talk, Professor Rehg will discuss AI approaches to measure and model social behavior. As a quick note, we will be recording the presentation today, and we'll ask that you hold your questions until the end of the presentation. Take it away, Jim.
Awesome. Thank you, Ben. So it's a great pleasure to be with you all today to talk about some work my lab is doing in understanding social behavior from the perspective of AI and sensing. A lot of our work is motivated by an interest in autism, which is a behaviorally defined condition that results in impairments in social interaction and social development. You can see some of the statistics about autism here. It's probably familiar to many of you. And I understand that the center is focused on the opposite end of the developmental spectrum in some sense, on aging and concerns of aging. I believe there are lots of interesting parallels there, actually, we can explore, and I'll be trying to develop some of those as I go forward in my talk. So in terms of what AI and technology might do for autism, there's a number of different things that one might identify. So one of the basic challenges that we have right now is recognizing the signs of autism early enough to initiate early intervention. And there's a body of literature that suggests that the earlier you can intervene, the more effective you can be with those interventions. But in the US, the median age of diagnosis is still essentially around 4 years of age. So it's really quite late in time. And if we could have some objective way to look for those subtle signs using sensing technology, for example, then some kind of large-scale objective automated screening would be possible, which is currently not possible, for example. And then the second thing you might imagine is that when you're getting treatment, the treatments can be quite complex and individuals can vary quite a bit as far as which treatments they respond to. And you'd like to have an objective way of measuring whether or not an individual is improving with respect to their treatment. And again, because these are all behaviorally defined conditions, you're really looking for subtle signs of behavior. You're looking for potentially subtle changes in behavior over time as a way to measure efficacy. And so the main theme of this talk is that AI models and tools can be an effective component of a solution that would involve ultimately large-scale objective measurement of behavior. And so, video-based and audio-based recordings of social interactions end up being a really important tool for accessing this type of data. So with that context, you can kind of outline a pretty straightforward research program, actually, which my lab has been following for the past 10 years, more than 10 years at this point. The literature gives us a rich list of constructs and building blocks from which social interactions are constructed, and often is able to put those blocks in a developmental perspective, understanding when they emerge and how they emerge in development. And the challenge is simply to measure them, to reliably and accurately assess these different constructs of communication and social interaction whenever they occur. And there's a variety of instruments that have been invented in the autism community, like the ADOS, for example, to assess these types of social processes. And we can leverage video from those instruments for automated analysis. So it really becomes a question of how to do this automated analysis in a way that is accurate and effective, and then to the extent that we can, also preserves the privacy of individuals. All right, so I'm going to go through a bunch of topics in this talk to kind of give you a sense for where we are with respect to this research program. And as you'll see, there's a bunch of things relating to attention, which is one of the most basic social processes, and one that we've spent a lot of time, studying. And then I'll talk about some more recent work looking at social interactions themselves. And I'll end with some newer work around using some AR technologies to support individuals with various needs that might be of interest. So the most basic thing is attention in some ways, visual attention being the obvious one because you can see the eyes. So it's an example of an overt, signal for attention. And it's an important part of social interaction. And the most basic question you might ask is, if somebody is looking out into the world, where are they directing their attention? And of course, nowadays with a wearable eye tracker that's available in many AR type of glasses platforms, this is a relatively straightforward thing to transduce. But we worked on this a long time ago before eye tracking was really a, kind of a widely available thing. And we asked this question, if we simply have the egocentric video of a person looking at the scene, could we estimate where they're looking? And the reason that we, focused on this is we really felt at the time, this was back in the early 2010s or so, that this egocentric perspective was really important. That if our goal was to understand human behavior in naturalistic contexts, daily life settings, we really had to observe the world from the perspective of the person whose behavior we're interested in. And that perspective, first-person perspective, is sometimes called egocentric perspective. And we were one of the early groups to kind of create this subfield of computer vision known as egocentric perception. Besides the importance of this viewpoint, it's also a practical reality that people are most likely to bring sensors into their daily life by wearing them, and a logical place to wear some type of camera-based sensor is on the head, which means you're essentially capturing this outward-facing view of the scene. So there are both sort of psychological and practical reasons why head-worn cameras are an interesting platform for this kind of research, and that motivated our kind of foray into egocentric vision. So one of the first findings that we had in this area was the result I'll show you here, which is the ability to process a video like the one you're seeing. So it's collected in a laboratory we had at Georgia Tech at the time, and then just predict where people are looking. So in this example output, the little bullseye pattern is the prediction of our algorithm. This is all pre-deep learning, by the way. And then the little green circle is the eye tracker. So the eye tracker gives us the gold standard reference, but the prediction of attention is based entirely on just processing the pixels in that video. So this work kind of really motivated us to realize that we can do non-trivial kind of inference about behavior just from this first-person view of the scene. And we've built on that in subsequent work. And there's other work I won't show you that tackles the same problem from a deep learning perspective using our current modern kind of models, and of course gets better accuracy as you would expect. So then from there, the next thing we looked at was really moving more into social behavior. And one of the most basic social behaviors of interest is eye contact, which is face-to-face interaction, looking into your social partner's eyes. This is a key social behavior. It emerges early in development, and it's known to be impaired in autism, meaning children with autism make less eye contact when they're typically developing peers, and then older adults with autism often make eye contact in ways that are not effective in terms of social communication. And so it's known to be important. It's often the target of interventions. So you'd like to know if an intervention is allowing a child to be more effective in using these basic social building blocks. And our question was, could we measure it? Could we measure it reliably in these first-person kind of face-to-face settings? And there's lots of ways to measure attention. I've already covered eye tracking before, but the bottom line for us is we want things that are easy to deploy in naturalistic face-to-face settings, and ideally things that don't require the child to wear anything. And so when interacting with a peer, we can instrument the peer or the social partner, and then the child can be unencumbered. And that's the setup that you see here. So this is a kind of a standard tabletop interaction that occurs often in developmental assessments. And so the child is sitting across the table from the examiner. The examiner is wearing this first-person vision system, this pair of glasses with the camera right here in the bridge. And then just from the geometry of the setup, you can see that if the child is looking into the eyes of their social partner, into the examiner's eyes, then they're looking into the camera. And so that lets us define a very simple binary classification problem. Is the face directed toward the camera, or is it directed away? And that lets us classify eye contact. And we collected a large data set. You can see here all the green examples are eye contact positive examples, all the red boxes are negative examples. And this is a very rich data set of interesting behavior from children that we collected in the course of our project. So this is the performance of the method. Green means detected eye contact, red means no eye contact. And this is a typically developing child in our lab at Georgia Tech. We brought kids in to measure their behavior. And then this is a boy with autism at our collaborators' site at Weill Cornell Medical Center in White Plains. And he makes less eye contact in general, but when he makes it, we still are able to detect it reliably with this method. And so the big question for these kinds of things, so you've probably seen lots of results with AI models that are achieving very impressive levels of performance, on a variety of tasks. And the big question, of course, is really about accuracy and reliability. So does this method produce measurements that are consistent with human assessment of attention? Because that is the gold standard. And so for this project, we collected another data set of a similar tabletop setting. And then we had it rated by 10 raters that are trained to reliability. And then we measured each rater's agreement and disagreement with their peers. So each yellow dot is one of our human raters compared to the nine peers. And then we simply measure whether or not they agree and turn that into a precision recall curve. Okay, so this is like inter-rater reliability, but mapped into a machine learning kind of setting to visualize the results. And so the spread of these yellow circles is simply the inherent, uncertainty in assessing a social behavior from video. Even humans disagree to some extent about whether or not something is happening. In this case, it's frame-by-frame coding of eye contact. And then that yellow spread is kind of the uncertainty among the humans. And the green diamond with the little standard deviation bars is our AI algorithm. So this AI algorithm is right in the middle of the expert humans. And essentially, if I took out any one of the humans and replaced them with AI, then the reliability of that group of raters wouldn't change. And we deduced from that experiment that this model has human level accuracy, that it's as good as any human, any highly trained actually human in assessing this core social behavior. And I think at the time that we published this was the first finding around kind of human level accuracy in estimating a social behavior from video. And so this is kind of really just the project we're pursuing is to continue to do this, work our way through the list of all the constructs that are really important for each one, find models that are as accurate as people are. And then if we can succeed in that program, then we'll have the building blocks for understanding social communication in this purely, kind of automated, objective way. So the next thing we've been working on is looking at other forms of visual attention. So this is a more general problem. So you have an individual that you have identified. In this case, it's the woman in the top row of these video frames, and you just want to know in every frame where is she looking. And so if you can ascertain where she's looking, and then you put a green dot at that location, and if you can't tell where she's looking, for example, if she's looking out of frame, then you don't put anything. And so this is an algorithm that tries to predict visual attention from the perspective of looking at a social partner and asking where are they attending, which is a very important thing that humans do routinely as part of our communication repertoire. And we can do this assessment for each person in the video. So then the next row shows the same analysis, but performed for the man. Okay, so this is a pretty well-studied problem actually in my field of computer vision. We have some recent work that is under review right now that I think we'll get in, hopefully. Well, I shouldn't jinx myself. That's kind of the state of the art for this problem now. So this is the more formal definition of the task. So you're given an image, you're given a bounding box, that green rectangle that shows the subject of interest. Whose attention are you interested in? And then the output is some kind of heat map that shows where they might be looking, including a prediction of whether or not you can actually tell that it's inside the frame. And then the ground truth for this, again, the data that you use is human annotation. Just people go in and click where they think the person is looking in the image, and those clicks give us the data we need to train a model. So this is the early work on this model back in the mid-2015 that was pursuing this what's called a two-stream or two-branch architecture. The main idea here is that the scene itself gives you lots of information. There's this idea of saliency, things in an image that people are more likely to look at. You can assess that objectively through eye tracking studies, for example. And so one of these pathways in this model simply tries to predict the saliency. What are the things that people would be likely to look at if they could see this image or they were in this scene? And then the second pathway looks at the head and asks if this is the person that we're interested in, and based on their head pose and their eye configuration and so forth, where in this scene are they likely to be looking? Okay, so this is kind of the basic idea that really defined a lot of prior work until recently. And we had a model along these lines that was more complicated that my student published a number of years ago. And we also collected a data set at that time that was the first video-based data set for this task. But since that time, these models have gotten really complicated, okay? All these are different architectures with different modules that add additional cues like depth and estimating the body pose and so on. And this is kind of a trend that we had in the early kind of deep learning era, building these very complex, kind of highly specialized models, which continued, till recently for this particular problem. And such complexity is not great. It's hard to train these models. It takes a lot of different kinds of specialized data to combine them. And it's actually in contrast to where we are right now in other parts of computer vision, excuse me. And so here you're seeing a example of what's called a foundation model, which is a single large analyzer that's capable of building a rich visual representation from an image. And because of the richness of that representation, it can be used to solve multiple tasks. So rather than having a separate model for each of these tasks, depth estimation is predict how far away are the pixels in an image, given the image. Scene segmentation is take all the things in the image that are the same object and give them the same color. So you segment or group the pixels that come from the same object, and then you identify what kind of object it is also. These are all tasks that were studied initially separately with completely separate architectures, but now they're unified in this foundation model. A single representation can be used to solve all these tasks because the representation is rich enough to describe the visual world in a significant level of complexity. And so we asked what I think is the obvious question, why not do this for other tasks that involve social behavior? And it's not a trivial question because the people that built these models that I'm talking about, they were thinking about depth estimation and semantic segmentation. They were thinking about applications like autonomous driving, where you have all kinds of scene understanding tasks you'd like a single model to perform. But they almost certainly weren't thinking about children or older adults. They weren't thinking about social behaviors or other kinds of health-related issues. It was simply outside their radar. But these models are very powerful, so they might still be useful for this kind of task. And it turns out that they are. And so this is the work of my student, Fiona Ryan. And this is an architecture that she invented, which takes one of these frozen visual encoders. So it takes this Dynamo V2 model, doesn't train it or fine tune it in any way, just uses the representation that it was trained to produce. And that's where the money is, of course. Those representations are millions of dollars of expense and training to produce this representation of the visual world. Once we have that, then there's some downstream modules you see here on the slide that can be trained in a straightforward way with limited amounts of data. And those modules are sufficient to convert this rich representation of the visual world into a measurement of the thing you care about. In our case, the attention targets of a participant of interest. So there's some details in the logic here that I'll just skip over, but it is important to design this logic. So this representation by itself is not powerful. The power comes from harnessing it in a particular way for this task. And this is currently the state of the art for this task and is beating lots of models that are very complex, that are trained on many more complex data sets than ours and have many, many more parameters than our model has. And so I hope this is a pathway we can follow for many other works along these lines now that it's clear how to proceed. And I just want to show you the results of this model. I think you can see what the idea is, right? So that's a mistake right there. So it's not yet human level accuracy, but it's not bad. Okay. And then we did some out of sample testing. These are just other YouTube videos that we collected, and you can kind of see the performance. So this is not yet working well enough, I would say, to be just a reliable tool. And there are some challenges in estimating attention in general settings that I can come back to if we have some discussion. So there's some question about how to interpret accuracy and ambiguity in particular for these types of settings that are very complex. But I think this is a pathway forward, and I think it's pretty exciting. And just to make the obvious point that just plugging in these big analyzers in the kind of standard places in an existing architecture doesn't produce good result. In fact, it's worse than not doing that. So you really have to think about how to use these models. But once you think about it, there's a straightforward pathway. So one of the things that I find exciting about this finding is that having been in this business for a long time of trying to measure these behaviors, from sensor data, you always have this first step. You have to collect a large sample of data with some construct of interest, visual attention, let's say, and then you're always focused on just simply collecting enough data to actually be able to train a reliable model. And because that's a big lift to collect enough data, and because of that, you almost never get to ask the important question, which is like, is this data really representative? Does it really cover all the settings in which we might care about attention? Like those kinds of comprehensive assessments often seem so far off, given the challenges, just getting it to work at all with enough data to train a model. So now that we have this ability to leverage these existing pre-trained representations, we can ask these questions. We can ask, suppose that someone's going to give us a foundation model and we're just going to use it for this task. How can we ensure that the data set we're using for validation is truly representative, that it covers visual attention of children, in my case, or in this case, in a wide range of settings, across different cultural contexts, different ethnicities, and so on. And so now we're beginning a process of collecting that kind of data developmentally to then have a data set we can use to really validate these models. That's kind of an ongoing new project that we're starting with a number of collaborators in the autism and developmental space. And I think it'd be interesting to do this in other settings as well. All right, so I want to now move from, asking a question about, where people are looking, and then introduce some other modalities and some other constructs that are essentially built on top of the basic kind of social attention. So one of the targets for a lot of this developmental work is this concept of joint attention, which is this kind of developmental progression from just looking at a social partner to interacting with the social partner around an object or around some shared context in your environment. And this progression from mutual gaze to joint attention is well documented in the developmental literature, and it's believed to be an important building block for acquiring language and acquiring broader skill in social interaction. And once again, it's known to be impaired in autism, and then understanding exactly how it's being utilized by children is an important task for assessment. And this is just an example of some of these joint attention constructs looking between an examiner's face and object. There's a rich literature on this that I won't have time to go into. And this plot illustrates the role or the importance of this in understanding autism. So this is a graph of trajectories. Each trajectory is a single child with autism. And then at the bottom of the chart, the x-axis is their chronological age, so their birthdays. And then the y-axis is their language age. And this is normed. So the 45-degree orange line is typical development. Language acquisition progresses in lockstep with the child's chronological age. And you can see that kids with autism, generally speaking, are acquiring language, with much less facility than the typically developing children. Their language age is significantly below their chronological age. But there's tremendous heterogeneity. So some kids actually seem to be more or less aligned with the TD population, maybe even exceeding it in terms of their slope. But the majority of children are at a much lower rate of acquisition. And so early research in autism in the early 2000s asked the question, how could we examine a child at intake and predict which of these curves they're likely to be on, whether they're slow in acquiring language, whether they might be more close to the TD rate in acquiring language. The ability to tease this population apart into subgroups that are encountering different types of challenges could be really effective in tailoring interventions and developing more effective treatments. But it was very challenging to figure out what would be the defining or differentiating feature. People tried a lot of things that didn't have any predictive value, and then they tried joint attention. And it turned out this was highly predictive of language outcomes. And the evidence for that is this little plot here from Michael Siller's PhD work. This shows the same sample that I showed you earlier with some regression modeling, and now stratified based on the child's facility at a joint attention task at intake. And so the kids that have better ability to coordinate their nonverbal communication with a social partner well before they acquire language, those children are on a much better trajectory. They will go on in a better language outcomes 4 years later in this longitudinal study. So this was a really important finding. A predictive variable that tells you something about what could happen in 4 years' time is very difficult, developmentally speaking. That's a very long period of time. And this finding drove a lot of the research around, looking for joint attention as a possible, diagnostic marker, as a possible target for intervention. It was highly influential. And so one of our motivations then is to build on our success with understanding visual attention and then begin to model joint attention. And this is just an example showing these models that I was showing earlier, just showing how the model performs in this setting where kids are in a tabletop kind of examination setting. And then we trained a little model to try to predict joint attention. You see that on the right. That model is not super accurate. So there's still quite a bit of ways to go, I would say, to get joint attention to be a construct that we can reliably and accurately measure. But we're quite interested in working on that and have some new collaborations along those lines. All right, so that was kind of your progression from visual attention to joint attention, kind of going up in terms of the complexity of the interaction that you're modeling. And I want to now briefly mention some work on auditory attention, because I think this is very potentially relevant for this group and very important in general. So auditory attention is really hard, of course, to assess because it's completely covert. You can't look at someone's face and tell where they're listening or who they're listening to in a straightforward way. But it's extremely important. And in particular, I think when folks have hearing impairments, it's often would be very helpful if you could understand, who they're trying to listen to and what are the properties of their social environment that make listening challenging. And the first step in really getting insight into that is to understand in this very fine-grained way in a conversational setting where people are listening. And so my student, again, Fiona Ryan, did this work at an internship at Meta, and we published the first paper kind of on this problem a couple of years ago. And one of the key things actually for getting this to work, there's some architectural stuff that I'll show you a little bit more detail in a bit of a related model. But one of the hardest things, of course, is getting any kind of ground truth at all. So if you've ever tried to look at this, looking at a multi-channel video and audio recording of a scene and trying to figure out who's talking to who in in a very fine-grained way, like frame to frame, it's essentially an impossible task. So the way we solved this problem in this work is we actually had this kind of staged data collection. So people were, put in this room and they're wearing these wearable kind of egocentric headsets. This is all stuff that was done at Meta. And then they're given instructions. So they're divided into subgroups, and we tell them, if you're in this group, these are the only people you're allowed to speak to. And then if you're in this group, these are the people you're allowed to speak to. So we kind of predefine these little cliques of people that are interacting. Of course, the AI model doesn't know that that's the case. It doesn't know the cliques. So it has to figure out who's talking to who over time, who's listening to who. But at least we have the ground truth to know, what the pattern of interaction is. And so we collected this data set that I hope actually will be released sometime this year. It's been taken a while to get this released from Meta, but I believe that it's coming. And I think there's another data set as well related to this. And so then we did a follow-on work, which was published last year at CVPR, on going beyond just who's listening to who and looking more at what we call this conversation graph. And I want to just dig into this a little bit to kind of show you the basic idea. And this was my student, Wenxi Ji. I did this work at her internship at Meta. So now we're interested in kind of not just who is listening, who the first person is listening to. We'd like to take a multi-party social scene, multiple people interacting in different ways, and we'd like to understand their patterns of interaction based on the visual and auditory channels that we can collect. And so this is the basic way we decompose this. So you can think about a graph where people that are interacting are connected by edges. And then we think about this graph as consisting of edges that go from the camera wearer, the egocentric subject, out into the scene of their social partners. And we think about edges that connect people in the scene who are my social partners who are talking to each other. So we think of these as egocentric, me looking out into the world, and then exocentric, looking at things that are happening, interactions within the world, between people in the world. And we kind of use that perspective to decompose this graph into these two components, the egocentric component and the exocentric component. And when you combine them, you then get the complete understanding of the social scene. But it's important to point out all of this is being done from one person's perspective, from the perspective of the person wearing the sensor hardware. And again, that's really important because looking ahead to applications, you'd like to give somebody, for example, a smart hearing aid, they could wear it, and then as they interact socially, the AI agent could figure out, oh, you're listening to this person and talking to them. All these people that are there in the scene talking, and they're not relevant to you. So then I'm going to null out the sound from those people you're not trying to communicate with and emphasize the sound that, that is really meant for you. And if we could do something like that eventually and solve all the technical challenges of real-time, highly reliable, in a wearable form factor, these are major, major challenges, not to gloss over anything. But that could really be, meaningful and much better than kind of the current state-of-the-art fragmentation, which is more limited. So that's a motivating example for us and for the group that we were collaborating with. All right, so same setup as before in terms of data collection. The participants are kind of predefined in groups that are interacting with each other. Our job is to build this representation you see on the right, a graph that connects people that are interacting, and then directionality of the edges identifies whether you're speaking to that person or listening to that person or both. And that then evolves over time, frame by frame, as the recording progresses. And so there's some very complex deep learning architecture with all kinds of attention stuff in it. I'm not going to even attempt to try to explain this to you. But the usual thing about these findings is that the students that did this work, they tried all kinds of things in a totally brute force, exhaustive search kind of way, which is kind of how science is progressing right now in where we are. And then this was kind of the thing that was performing the best. And the main thing I want to emphasize is this is now a multi-channel audio, just like in the previous auditory attention. So we have spatialized audio. We can understand the directionality of the sound sources, and then we have the video as well. that we fuse with this architecture. And then this is the current state of the art as of earlier this year. So I'm just going to try to show you the result. It's actually quite hard to tell what's going on with these kind of systems, to be honest. But I'm going to play the clip first, showing you some of the interaction, and then I'll play the clip that shows the analysis results.
For us to do. Actually, we
Okay, so that was really short, but complicated cocktail party kind of setup like you would expect. And this is the algorithm's output. So on the right is the ground truth based on our this data collection procedure that I described, plus some coding of actually who's listening and who's speaking. And then on the left, in the middle rather, is the prediction of our algorithm. And so whenever the two pictures are the same, it's doing the perfect job. Whenever there's a discrepancy, the algorithm is making a mistake. It's actually quite hard to tell, even looking at this, actually, how well it's working. But it's working, much better than chance, put it that way, but still making quite a few mistakes, actually. So this is by no means a solved problem, but I think it's a good direction to work on. And I do think that these same kinds of objective measures for social communication involving language, which is especially relevant for older populations, anybody that's got language, older than some years of age, this ability to bring the language into the picture through audio is going to be really important. So we're very glad to sort of have this work that's moving along those lines. All right, so this is now we spent a lot of time talking about attention because it's the most basic thing in some ways, and it's also the thing we've worked on the longest. We have the most results, I would say, to show. But I'm going to now, as I move toward the end of my talk, I'm going to show you some things we're doing that are more complicated. So this is now getting into the actual meat in some sense of the interaction and starting to ask questions about, more deeper questions in some way about what's actually happening during the interaction. One way to think about this is we really want to progress beyond the kind of who said what to whom kinds of questions that, were kind of the original drivers for a lot of this early AI work. And now that we have made pretty good progress on those questions, we'd like to start understanding the meaning of the interaction to people, which is really important because obviously as a human, most of your time you're not even thinking about the act of communicating or attending. All that is subconscious. Your focus is on what the heart of the matter. What am I saying to this person? Why am I saying it? What does this person think is true or false about me, et cetera? And you're working on at that level. So we'd like to move our AIs ultimately to be able to operate at that level as well. All right, so we have this new paper with a new data set. I just want to get into it a little bit. So this is a project that ended a few years ago with Meta to collect a very large data set of first-person video. This is a very complex and interesting data set, more than 3,000 hours of first-person video from around the world, all kinds of different tasks. And then a subset of this video shown here features social interaction. So these are all videos of social interactions from the egocentric perspective. And in some cases, most cases, it's video and audio, and then some eye tracking as well. And this is freely available. You can just download this from a website that you can easily find by searching for Ego4D. This was quite an impactful project. And so I just want to highlight a little bit of the data we collected at Georgia Tech, and then I'll show you some things we're doing with it. So this is an example of people that we collected in the Atlanta area. These are folks who are at home. These are groups of friends, so they know each other, they're friends, and they're playing a variety of social games. In our case, these are social deduction games like Mafia or One Night Werewolf. Essentially, the property of these games is that people have roles that they're playing, but you don't know you don't know the roles of the people you're playing the game with, and then you got to try to figure out what their roles are, and they're trying to mislead you and fool you about what's going on. So it's this very complex social task of understanding, essentially who's what, who's who, and then whether or not you believe someone is, telling you the truth.
That's why I was thinking so hard.
This is quite a rich data set with different modalities, and then also pretty well annotated. And people are, doing all kinds of things, interacting socially, eating, drinking, et cetera. And again, this is all freely available to the research community. And so we looked a little bit at social deduction games from the perspective of persuasion. So one of the most basic things in these games is you try to get somebody to believe that something is true. And so one way to think about this in terms of constructs, this is a construct known as theory of mind. That your theory of mind lets you kind of figure out what the belief states of your social partners are, what they may believe, what they may think is true about the world. And then part of our interaction as social agents is to try to understand our social partners' belief states and possibly influence them in different ways. And so that's what's happening in these games. You're trying to guess what roles people have, and you're trying to influence what they believe your role to be. And so this is an example of how persuasion strategies might work in this game, just to give you an example.
What are you?
Villager.
Villager?
Mm-hmm.
What are you? I'm a seer, and I looked in there, and I forgot what the card.
So this guy's trying to lie about his role, but not very successfully.
Well, I hate to tell you, Chief, but you're not the seer.
Damn.
Ooh.
Yeah, also, if you're going to claim to be the seer, you need to be...
You gotta know what's
Yeah.
If you're in for
Yeah.
money, you have to be in for
So, this is a typical interaction in these
That's
games,
fine,
and it
'cause you're a
really,
villager.
the heart of it is really the ability to kind of
You know what I'm
understand
talking
whether or not you trust people and what they're
Wait,
saying,
what?
and in the context of this game,
So
what
he
you
would-
can believe. And so we have a data set we collected, including both these first-person videos and also some YouTube videos of these games, quite a few videos of these games from YouTube. And they're all annotated with respect to these particular persuasion strategies you see here. And then we have all the transcripts as well. So we have the language as well as the video and the audio. And then the challenge for an AI model is simply to look at this, multimodal data and try to identify whether or not a given persuasion strategy is being used. And so that's how the analysis would proceed here, looking at all the modalities over time for all the individuals that are there in the video and then also in the transcript. And the bottom line is that this is a pretty hard task. So the performance of AI in this case is not very high. You can see the numbers at the bottom here for predicting how somebody's going to vote at the end of the game, what they believe to be true about the status of the werewolves. But this is the first data set really of rich multimodal social data where you can actually tackle this problem. So this is kind of the first, I would say, truly kind of naturalistic multimodal theory of mind kind of task that has data available. And then we went on and looked at some other tasks that are related to this more basic kind of low-level tasks around social communication, identifying who someone's talking about in a conversation, pronoun co-reference resolution, which is a basic task in natural language processing, but which can be significantly improved if you have access to video. And so these are tasks that allow you to combine the language and the video together. And then because you can fuse these modalities, you can actually speak with more certainty to these kind of complex patterns of ambiguity and meaning in conversation. And this is a data set, again, that is built on our previous one. And all these annotations are freely available. You can just grab this and download it and work on it. And there's some architecture here as a baseline. One of the challenges is simply to link the modalities to identify the person that's speaking in the transcript, figure out who they are in the video, where they are as a person, as a bounding box, and then be able to, in doing that, bring the multimodal fusion to bear on this task when it's a very complex, multi-party, multi-person interaction that's taking place. So you can take a look at those papers for a little more of the details of that. So this is, I would say, work that's in its early stages. So I think going beyond the superficial, who said what to whom, and actually asking about the meaning of the interaction, what's the purpose, how effective was it, what was the significance of it to an individual. These are questions that we'd love to be able to answer computationally. We're obviously, not nearly as far along with those as we are with the more fundamental questions. And then I want to just conclude by showing you one new work that we're just getting started at UIUC around imagining how some of these tools might be useful, not just to understand what's going on in the context of an interaction or a task, but perhaps begin to think about providing some supports. Okay, so I'm very interested in looking at individuals with special needs that might benefit from a variety of AI supports as a part, probably a small part of the overall, supports and treatment and help that they're receiving. But I think there's an opportunity, since these platforms for augmented reality are coming, there's an opportunity to really harness them for these populations that otherwise are probably not going to benefit necessarily from these technologies. And so you can think about easily, many things that are interesting. So there are these AR glasses. I'll show you a few of them here. Whether or not any of these, live to see the light of day or survive, this is a trend in technology that clearly is evolving and is clearly, I would say, coming. And the question is, when will it become, usable? And we'll have to wait and see. But we want to get ready for that in terms of the technology that we're building. And then the other one is the hearable direction, where you have these very smart, kind of little bit of a smartphone kind of thing, but it's in your ear, and it can, again, process the audio in various ways and use that to communicate. So both vision and audition are amenable to augmented reality via these platforms, and we'd like to understand, how to utilize them effectively. So we had a paper that appeared at CVPR this year, and it's just a beginning of a work along these lines. And we framed it in the following way. So you kind of, this is the framing just for the computer vision community. This is not relevant, I would say, to children or to older adults necessarily, but just a kind of a thing to think about. So suppose you want to get help in performing some task in your daily life. So in the example, the user says, I'm trying to wash my trousers by hand. How do I do it, in my current situation? How should I proceed? And if you ask that question to some standard language model, then you get, actually a pretty good response. So these language models understand lots of things about how to do tasks in daily life settings, and they'll give you a pretty good, answer as to how to go about it. But of course, it's not in your context, right? It's just an abstract description, like a recipe. And then to use it in your own actual daily life context, you've got to translate that description, read it first of all, and then map what you read into what's happening in front of you. So that's not very helpful. You'd like something that was more directly supporting what you're trying to do. So then if you're wearing a camera, wearing a pair of AR glasses and there's an integrated camera, then you can capture a picture that shows what I'm doing right now with my hands, where the garment is, what's going on at this moment in time. And that should be more helpful. And if you take that image and combine that with a text prompt, and pass both of them to a VLLM, one of these LLMs that has a vision analyzer as part of it, then you'll get an updated response, which you see in the middle there. And that's also, accurate, helpful description of what to do. And now it's grounded a bit better in the context of what it is that you're actually doing. So these existing VLMs are already very good at taking image plus a question, and then generating a response. And if the image is from your point of view as you're doing some task, the response is more likely to be helpful, for what you're doing right now. But the disadvantage of this is you still have to read it. And even though it's tailored to your situation, you've got to map the constructs as you read them into what it is you're actually doing, which is potentially not that helpful or not as helpful. So then the last thing, which is the target of this paper, is given the image, given the prompt, can you generate an image? Can you manufacture an image with the property that it shows you exactly what you should be doing? So the image has your hands and whatever else is there in the scene, and it's illustrating this is what you should do to solve this task. And so this is an example of the image that our model was able to generate that provides the direct kind of visual instruction back to the individual. And so this is, I think, exciting to us because then, with the ability to display things in these glasses, you can then begin to connect what it is you should be doing as a process to something which is a really potentially very useful prompt that could then be delivered in some daily life setting. And you're probably not in practice going to show an image. I guess if you had a tablet, that might be an appropriate thing to do. You're probably going to think of other ways to display this information to help someone out. But the key is to understand the context and how to manipulate it, appropriately from a visual perspective. And that's what this work is getting at. So this is frame synthesis, egocentric frame synthesis. And so there's a bunch of reasons why this is not a trivial task, even though these VLMs are very powerful. One of the problems is that the kind of state-of-the-art data sets for this task are largely collected from the web or from YouTube, and they're not super enriched for first-person data. So this first-person viewpoint, particularly daily life settings, are not as representative as we would like in these online repositories of media. So then there's this translation gap, or what's called a domain gap, between the kind of web data and this first-person data, and the model has to bridge that gap in order to do an effective job of synthesis. And then the other challenge is that we don't have enough action labels that are rich enough to really describe what's going on because these data sets are annotated in relatively straightforward ways. And then there's solutions to this problem, and it's the usual story today, which is that we're using an LLM to analyze the scene. We're using a separate LLM to generate the things that the other LLM needs. And it's this constellation of these LLMs operating in different ways that ultimately provides the solution. All right, so then there's a big complicated architecture. Again, I'm not going to get into the details of this. That involves different kinds of instruction tuning with some representations that are frozen and some representations that are being fine-tuned. And this is kind of currently the state of the art in general in this area. So we're doing the same thing everybody else does with regards to the methods. I'm just going to skip over that part. And then, one of the challenges in this area is assessment. So in the end, you're producing an image. We really don't have very good, metrics for assessing these images as to whether they, in fact, are capturing the right thing. So there are some metrics here that we're using, but they fall short of, a comprehensive characterization. So a lot of this assessment in the end is more qualitative. But based on various assessments that we tried, kind of the state of the art in this area, we're doing better than other kind of baseline methods. I just want to show you the results to give you a sense of how it's working. So here's an example. So all these examples, by the way, came from two data sets, the Ego4D data set that I mentioned earlier, and then a previous data set called Epic Kitchens that came before it that was just cooking kind of scenes. And then what you can see in these examples is the input frame is just all kinds of real life people performing tasks in a variety of settings. And then there's the prompt. You can see below what the person wants to achieve. And then on the second row is the generated frame that was produced by the algorithm. And so the part of this that I would call out that I think is pretty interesting is that this approach is able to generalize pretty effectively across a wide range of settings. And so this is not probably surprising because we've seen that these video generation models and image generation models that are available in general are able to handle a wide range of visual content. But this really hadn't been investigated for the first person viewpoint before, and it was possible that those domain gaps I referred to earlier might be a barrier, and this model might just break down for certain, first person settings that were uncommon. And it looks like that's not the case. So it's encouraging in that regard, because again, this first person video that we collected in this project, Ego4D project, it's very expensive and time consuming to collect. Anything that has to be collected from human participants, is expensive and time consuming. So it's heartening that we can take these models that are trained on massive quantities of web video, internet video, and then specialize them so they're useful for this specific setting of egocentric understanding. And then the last row is the ground truth. This is a representative frame from the actual video a few seconds later when they were performing the task. So this is a kind of a qualitative comparison. You can kind of see how close to become to what ended up being done by the individual that was performing these different tasks. And these are kind of cherry-picked examples here, and they all look pretty good. I'm sure my student could find ones that look less good. I should actually ask him to do that. This is my student Bolin Lai's work from an internship he did at Meta. But so again, I don't think this is yet ready for prime time in terms of being, working well enough to be put in front of someone, and actually used as part of a solution for someone. But I think this is a step towards that direction, and would love to continue to push this forward and then think about very specific, either clinical or developmental settings where this kind of technology might be, useful. I'd love to obviously talk to folks that are in the audience here about that if there's interest. So that's the bottom line for this effort. So let me just wrap things up, and I can take your questions. I just want to thank our sponsors over the years, many different very generous funders for this research. And then I want to thank my collaborators at Georgia Tech and Weill Cornell, and then some of my students are now at UIUC as well, like Wenchi, for example. And then just to wrap things up, I would make a couple of arguments. I think that there's this perspective of the world that comes from, cameras that are worn on the body, and this is called the egocentric perspective, and I think it's really important. It's how AI should understand the world, because in the end, they need to be helpful to people, and ideally, they're helpful enough that we choose to take them with us in our daily lives, and then, they provide us with some useful information and supports. By combining these modalities, we can get at all kinds of dimensions of communication, both verbal and nonverbal. And for the really young kids, the nonverbal is really critical, but really nonverbal is critical for everyone. And now that the verbal communication is working pretty well, I think it's really time to double down on the nonverbal piece and really bring that up to where it should be. Then we can have a comprehensive sense of how communication is happening. And these foundation models that are coming from the big tech companies and what have you, the good thing is that even though these companies don't care about kids in any kind of explicit way, they don't care about senior citizens either, but the good thing is their models are rich enough that they can speak to all kinds of problem domains these companies didn't care about and may or may not care about. And so because of that, we can take the fruits of their labor and we can use them for populations that we care about. And I'm really heartened by the fact that seems to be possible. And I think it will accelerate in a tremendous way research along these lines. It's very exciting. And I think we can do a lot in AI in working with these populations with special needs and other considerations. Obviously, I'd love to collaborate with you on that and find like-minded researchers that we can and talk with you. So please reach out to me if you're interested. Thank you.
All right, great. Thank you, Jim. That was very nice. So I'm going to invite Center Co-Director Deepak Gunnarsson for a first question. And then I'll ask other folks to queue up by raising your Zoom hand, and we'll get to as many people as we can before we run out of time. Deepak, go ahead.
Jim, this is a really fantastic talk. I really enjoyed all the very interesting work. So I'm curious, lots of questions, but one thing I'm curious about the last part that you mentioned is, to what extent do you think you can bridge some of the data, the lack of egocentric data sets or the difficulty in collecting them with just synthesizing data? I'm curious to what extent the modern language, the LLMs or VLMs already understand enough that you can just use synthetic data from YouTube,
Yeah.
right? First person.
Yeah, it's a great question, and we've been thinking about that a lot, obviously, and so I think it's still a bit unclear exactly how far they go. I think our project gave us some initial insights, and my concerns were that this would really fail spectacularly, and then that turned out to not be the case. But at the same time, if you look at those images closely, you'll see that they have many of the artifacts we associate with generative AI today. Hallucinations, the hands don't look great all the time. Sometimes the number of fingers is wrong, that kind of thing. So there are kind of well-known artifacts in these generative AI models, and we inherit all those problems when we adopt these tools. And that's a big challenge for the field. So I think the data domain, I'm less worried about the domain gap. I think we can probably work on that. If you're going to use the data you generate for model training, then the presence of these artifacts and hallucinations is potentially problematic, because then it really changes the nature of the distribution of the data that you're trying to model. If you're using these models for other purposes, more for instructional purposes or other kinds of interventions, then maybe there's a way to ameliorate, the issue of these hallucinations. The other thing I would mention is that when the goal is pixel output, then the resolution, is going to become a concern. Like, probably you're going to have to generate images at a certain resolution for them to be useful and acceptable to people. And there's a big computational cost associated with that. So I think finding ways to, on the synthesis side, to ameliorate the cost of computation, maybe you generate an intermediate representation that's not an image, and then you render it, to get an image. That could be much more efficient computationally and could give you a high resolution potentially, and still preserve the fidelity of the output. So I think there are ideas along those lines of how to deal with the computational requirements of these models on the synthesis side that are also worth exploring. So really a lot of interesting questions to explore here, I would say.
All right, thank you. Adam, you're up next. Don't forget to unmute.
Hi, sorry, I'm on my phone. I'm just curious very much about how you were able to, and might be able in the future, to access some of this data that was provided by a company like Meta. We're looking mostly at language samples to understand various kinds of behavior. Think about loneliness or resilience or things like that. And so one of our challenges, like yours, is acquiring enough human data to be able to drive the kind of training we need to do. And I'm just very curious about how you were able to do that, and are there some tricks to get that to happen?
Yeah, so I think, the key thing, just to kind of state the context in a way, is that, these companies that are collecting this data right now, they have no obligation to reveal their sources or make it available to anyone. And until they're forced to do that, by law, they won't do it. So the data essentially is not available unless something changes, in a kind of political or cultural context. The good news is that these companies, for the time being at least, are willing to release their models, either directly in the form of, model weights you can take and download, or indirectly through an API, like is the case for OpenAI. And so then, the fruits of those models in some sense are available to you. Now, if all you have is an API, that's actually very limiting. So the work that I was showing in my talk mostly requires the ability to access the model weights and then train other logic, on top of those model weights that extracts and utilizes their information. But again, the good news is open source is very much alive. So you probably all saw the DeepSeek excitement in the past week or so. It doesn't look like the open source models are going to be dead relative to closed source anytime soon. So I take that as really very heartening, as long as there are folks out there with resources that are going to train and release big models for public, use and public consumption. I think this enterprise can continue. And so then in that case, the game is you get the data indirectly. You get the models from the companies. The companies have all the data. They spend millions and millions of dollars to train a model, which takes that data and compresses it down into these model weights. And then, the good guys, release the model weights for everyone to benefit science, to benefit the world. And then we take those model weights and we use them for our tasks. So you get the data indirectly through the model weights. And then you need the specialized data you referred to that speaks to the specific constructs and questions that you actually care about, because the model doesn't know anything about your constructs or your questions. It just knows general things about vision or audition, And then through your specialized data, which is going to be inherently small in number, but luckily you don't need a lot of it, that's how you then get the model that you want to have to solve your task. And so that's what we've been doing in all the papers I was showing you, and you can do that too. That's the paradigm of the day, I would say.
All right, very good. And I think that takes us just about to time. So I'll say thank you again, Jim, for presenting today. If anyone missed the beginning of the presentation, we'll have a video up on the Mass AITC website shortly, and be on the lookout for the next webinar announcement for next month's webinar. Thank you again, everyone.